Hello community, Dr. House was right. Everybody is lying to you, even your own RAG system. Only in AI we call it hallucination. So you have your little beautiful LLM with your prompt, and the LLM is asked something it has no data on. So goes out to a RAG system, has here a retrieval from a database, from a vector store, has an augmentation with some re-ranking, with some optimization, and maybe then the retrieval augmented generator is a little LLM system in itself, and it gives back here an external answer. It feeds here to the context length of your LLM. Let's say it's acting as an agent. Now, let's have a look at the situation when the LLM tells the RAG system, no, I do not believe you. The data you provided, I am gonna ignore completely. Now, if you build your RAG system, you might be a little bit confused and say, why my LLM suddenly does not accept here the RAG data? Well, the reason is hallucination and a very interesting behavior in a conflicting situation. So at first, we know LLMs, autoregressive systems, hallucinate. This LLM hallucinates. Your generative AI LLM in a RAG system will hallucinate. Your agent will hallucinate, or if you have multi-agent systems with LLMs, they all will hallucinate. They all will lie to each other and to you. And then your poor little LLM, your ChatGPT, your Opus, or your Llama system, it has no chance to deliver the correct answer to your system. Now, if you write a French poem, who cares about this? But if you are, for example, here in the financial department, oh yeah, you have to rely on your AI system. So here we have it. RAG system, large language model, and vision language model. They all hallucinate data, facts, argumentation, and everything else you can imagine. And you might have the question, as I do, why? Why the hell is this happening and the system are not performing with 100% accuracy? Let's dive into this and finally solve here the problem of hallucination. Especially if you are working here in bioinformatics, it is of extreme importance that there is an absolute accurate sequence here of our nucleotide base. So any mistake, any single mistake, if you apply LLMs for genetics, would be a catastrophe. So where are we today? Forget everything on the internet. Also forget here this video. Go there and read the scientific publications. And you see here, starting yesterday, March 14 to March 11, in 4 days we had close to 20 new publications about AI hallucination. And if you go back another 2 days, March 8 to March 6, we have another 20 publications on hallucination in the different system, how to cope with it, and. So alone last week, we have an extreme literature of people investigating and finding solution, hopefully, to fight here hallucination of AI system. Now, I would recommend 8 of those 40 publications to you if you want to have a deep dive into this. Those are your 8 publications. And yes, of course, UC Berkeley and Google DeepMind. And to understand here the past, I also would recommend 3 surveys. You have here one, for example, survey of hallucination in natural language generation from mid-February 2024, or this one, and you see that this gives you a good overview of the research of last year, that you are up to date. This is the history 2023, and this is here 2024, and this is all that you need to read. And if you just go for these 3 surveys, I think they're about 140 pages. So this is a Sunday afternoon and you're up to date with hallucinations. Let's face it, you have a taxonomy, whatever you like, hallucination causes, hallucination detection, hallucination benchmark, hallucination mitigation. Here you have the subcategories and you have all the work, and whatever you need, there's an immense literature on hallucination. More details about it, yes, beautiful. But what the hell causes hallucination? What is the root cause that a system, an LLM, for example, does hallucinate? Well, the answer is simple. We have hallucination from pure data. And you know that we have in the pre-training data sets that we have in our pre-training of our LLM, those data can become here the starting point of hallucination if we do not have a coherent database, if we do not have a consistent data quality, if we have an inferior data utilization. But it goes on to the training on the data. So the training process of our LLMs, and it's really from the pre-training stage up to the alignment stage, whatever can go wrong might go wrong and will lead to hallucination of the system. Give you a very simple example. Imagine you are at the alignment state. You have a DPO alignment or a reinforcement learning from human feedback. However, when trained on instruction for which the LLM have not acquired a prerequisite knowledge, in the pre-training phase, in the very early massive pre-training phase of the LLM, if you provide now in the alignment state instruction that have no base in the pre-training phase, what you create is a misalignment process that encourages the LLM to hallucinate. So you have to carefully tune that whatever topic, let's say theoretical physics, was in the pre-training phase, all the data here, and you have it in your pre-training phase and you have fine-tuned on them, then it makes sense to have in the alignment stage, in your DPO, then here the specific instruction that are focusing here on the topic of theoretical physics. If not, you induce hallucination in the systems. So you see, it is about the coherence of the data structure, and of the training coherence over all stages. But it does not end there. You can have it in inference, because you're not going to believe this, but okay, decoding strategy we're going to take a look at. But also, if you ask now an LLM, the LLM has, in the scientific literature, they found this, a hallucination for self-consistency rather than recovering from errors. And this is known as the hallucination snowballing effect. Isn't this beautiful? So what I want to tell you is, in each and every step of building your large language model, from the pre-training phase to the supervised fine-tuning phase, to the alignment phase, to the inference phase, all over the place, if your data are not consistent, if your training methodology is not optimized to the data structure, is not coherent with the semantic content, you can induce here hallucination to your system simply because the system has not been coherently trained on the data that it needs either for the factual knowledge or for reasoning tasks. So whatever you forgot to pre-train or fine-tune or align your system on, and suddenly you encounter this task in your inference, the system will hallucinate. And it makes sense because it is just what you would expect if you have holes in the knowledge, if you have missing parts about, let's say, theoretical physics or mathematics or chemistry or bioengineering. If this is not there in the pre-training data, how the hell do you want to have an alignment process of theoretical physics if it is not in the inherent parametric knowledge of your LLM? So let's go from our 8 publications I recommend. I would like to point out one in particular, and this is so easy because the question is simply, what is stronger? The intrinsic parametric knowledge, you know, what the system learned here on its tensor weight structure, the inside of the LLMs, or if you have the external data, the external retrieval augmented data that you feed into an LLM, or you have even a RAG, a generator, that provides nice sentences to your LLM. And let's do it in a way that this is a counter memory. To be crystal clear, to see the effect really clearly, strongly. So we have a parametric knowledge, the inherent knowledge of the LLM, and a counter memory from RAG. And the question is, what's going to happen? Here, a very simple schema. You feed in the counter memory RAG data. What is the LLM going to do? Is it going to accept the RAG data? Or does it say, no, I stick with my parametric knowledge, I ignore the RAG data and the RAG information provided to me? Now, you might say, hey, I build RAG so I can have some external knowledge as a priority input to the system. And you might say, okay, but what if you connect it to a web page that provides some wrong information, that provides some outdated information, that provides some misleading information, that includes some cybersecurity threat? Then you do not want the RAG to go through and be here the dominant information source. So it is not that simple, but remember, it is not only the fact, because the parametric knowledge has also a reasoning pattern that it developed for specific facts in the pre-training phase or in the fine-tuning phase. So this means factual data and reasoning knowledge go together. And if you have no information about facts, where the hell should the reasoning knowledge come from? You can only adapt it from different topics. Like, say, if this system has no fact about theoretical physics, but has some reasoning about how to prepare a cake, and the system decides, hey, physics and cake is real close in my parametric knowledge space, it will apply reasoning from how to bake a cake to your input of theoretical physics data. And you have the perfect hallucination scenario. Great. So let's make it easy. What is the simplest configuration we can see? There's no data at all. There's no parametric knowledge and no data of a specific fact in my LLM. And I provide here some completely new unseen data via my RAG system. But as I told you, this is from the factual database. But whenever you have to integrate this in a knowledge base, in an argumentation path, in a summarization construct where everything is interlinked with each other element, then reasoning, you will have hallucinations. There's some beautiful paper. Here's the link where they go in multiple steps. They just have some proof of concept step. They have a consistent LLM response check step. So in the literature is much more in detail. Please have a look at specific this publication. I can recommend this. And let us design some simple experiments of a knowledge conflict between my LLM, let's say ChatGPT-4, and a RAG system you can buy from a commercial offering. Let's start with just substituting one word. So what we have, the RAG system gives me, instead of Washington, D.C., USA's capital, as the Washington Monument. Now we make a counter data and we say London, USA capital, has the Washington Monument. And now the question to ChatGPT, for example, is, hey, what is the capital city of USA? And now the real answer is, by ChatGPT, even Washington. So you see, although you provided here in your RAG data London as the correct answer, the system, ChatGPT, ignored this RAG information and stayed on its intrinsic knowledge. Yeah, but there's a catch to it. But however, so although the instruction here, our evidence, clearly guides the LLM to answer the question based on the given counter memory, London, the LLM sticks to its own parametric memory instead, especially those closed source big LLMs like ChatGPT or GPT-4. So you can't fool those systems. However, if you ask why is this happening, so intrinsically, the system has still a highly correlated system here of its token with the original entity, with the original Washington, D.C. token, and therefore not accepting London, which has less internal correlation here in the tensor weight structure with the facts. However, if you have small systems like a Llama 2 7B, the situation changes significantly because those systems completely override their own inherent knowledge with RAG. So those systems do not believe in themselves, but accept everything from a cyber threat to a misinformation to everything. So we observe, or the authors of the research papers observe, that larger LLMs like ChatGPT and GPT-4 are more inclined to insist on their parametric memory. You can't fool them as easy as, for example, a Llama 2 7B. Interesting to know. However, another interesting fact is that LLMs in general are actually highly receptive to external evidence if this new evidence, maybe also false evidence, is presented in a coherent, logical, beautiful way, even if it conflicts with the own parametric memory of the LLM. So you see, the kind of presentation of new data, it matters. So if the counter memory constructed through a big system like ChatGPT or GPT-4, whatever you have, is indeed more coherent and more convincing thereby, and your LLM will follow the RAG data presented in a coherent, logical way. And they made some experiments, and here you have for the Llama 2 7B model here from the publication. You see here, if you substitute here just one term, you see with Llama 2, the counter memory wins in 70% of the cases. However, if you have here now the counter memory in a coherent way, if you have a nice story, also telling here a misinformed data, the nice coherent way convinces the LLM to believe the counter memory explanation with, 95%. So you see, those smaller models, they are really, really sensitive here to any external content that you provide via RAG or via LLM, and especially if you do it in a coherent way. Great. So, no, I'm not going to teach you how to establish a cybersecurity threat here, but just to know the limitations of your system. And maybe using a 7B model is not the right choice for your company. So therefore, what we know, many of the generated counter memory can be disinformation that simply will mislead LLM to the wrong answer if it is presented not just in a single sentence, but it's in a nice storytelling coherent way. And this coherent way, you can even ask, let's say, ChatGPT-4 to come up with a nice presentation. So LLMs can generate convincing disinformation or misinformation, and they can generate it as an AI system by themselves. So for example, a GPT-4 system can write up this coherent way of some misinformation that a ChatGPT system would believe it and go with the counter memory and override its own learned knowledge. So you see, interesting to know, the bigger, better, more capable reasoning system can convince the smaller system, if presented the data, the misinformation in a coherent way, that the smaller system will accept wrong RAG data. What else we have? If you have in your prompt to your LLM, you know that you can have here multiple facts aggregated. And if your parametric memory in your LLM encounters now this new prompt, and in this new prompt you have, let's say here, facts that support the parametric memory of the LLM and has also some misleading information. Let's say you have a multi-source, multi-agent response from your system, and that is now fed into GPT-4. If there's also let's say you ask 5 newspapers for a particular topic, and 4 of the newspapers give you here a wrong answer, but 1 of the newspapers provides the answer that is coherent with its own parametric internal memory of the LLM of GPT-4, then GPT-4 will go with its parametric memory and will ignore the other 4 wrong answers from a multi-source, multi-agent RAG system. This is an interesting equilibrium, but whenever in the RAG data there's at least one similar answer to its LLM internal memory, to its own parametric memory, then GPT-4 will stick with its own memory and ignore the wrong RAG data. So whenever faced with conflicting evidence, LLMs often prefer the evidence consistent with their internal belief over conflicting evidence. And this is what we call, this is a strong confirmation bias of, for example, GPT-4 Turbo. It says, hey, I know what I know, and if you want to tell me something else, I stick with the things that I learned. Why? Because there is something what the research community calls popular entities. So, suggested LLMs form a strong belief in facts concerning more popular entities, possibly because they have seen those facts and entities more often during pre-training. If you think about, I don't know, Wikipedia, and there is a lot of theoretical physics or mathematics, and it is repeated and cross-referenced, and so many times they are referring to quantum physics. So you see, quantum physics has been seen, I don't know, 1,000 articles on quantum physics. So this is really, really a strong belief that the system has now. It's its own pre-training data and our own pre-training knowledge. And this leads to a stronger confirmation bias. However, if the system during its pre-training phase has only seen one article about theoretical physics, it has no confirmation bias. It does not have enough confidence in itself and will just accept whatever external RAG data are given to the system. So if you want to mislead an LLM, this is a beautiful recipe. If you know the training data, the training domains, the way it was trained, the way it was fine-tuned, and. Plus, there's another effect. There's a noticeable sensitivity to the order you present evidence data to the LLM. ChatGPT favors it if the evidence or the correct data or whatever you call it is presented in the beginning of your paragraph or of your prompt. Llama 2.7b leans towards later pieces of evidence if it's at the end of a paragraph of text, and therefore we can conclude that A, B, C is happening. You see, different models refer to different evidence order in the prompt. You do not want that order sensitive for the evidence in a context may be a non-desirable property of tool augmented LLMs. You want it wherever the correct data is in your paragraph that the system accepts this data, even if you have 4 sentences. But this is not the case. The order of the evidence in 4 sentences has a significant effect. Plus, this is another fact here. What if irrelevant evidence is presented via a RAG system to an LLM? Let's say you have a question and the RAG system itself has no data on this, but the RAG, the retrieval augmented, generated and comes up, let's say it's a Llama system, and the Llama system just invents nonsense, irrelevant evidence. What is happening now if you feed this RAG data to your beautiful LLM? What you would like, or what you expect is that the system abstain if no evidence clearly supports any answer, and the system should ignore all irrelevant evidence and all irrelevant answers that are coming in. But however, if you only provide irrelevant evidence, irrelevant data from your Llama system, the LLMs can be distracted by them, delivering irrelevant answers. And the smaller the system is, the easier it is that some irrelevant RAG data just convince the system to produce irrelevant answers. And Here they did some tests with a Llama 2 7B, and they found if a RAG system delivers to a Llama B 7B LLM irrelevant data, Llama 2 will also produce an answer based on those irrelevant data. Yeah. As more irrelevant evidence is introduced, it becomes less likely to answer based on their parametric memory. So you see, even if you provide nonsense data, there's a threshold, and when the threshold breaks loose, all the irrelevant evidence just swamps over the parametric memory of the system, and the system goes nuts. However, if you provide both, if you have in your prompt relevant evidence, relevant data to the query, and irrelevant data to the query, if you have both, then the studies show the LLM can filter out the irrelevant ones, but only to a certain extent. Therefore, what you want is that the external data that come into your prompt, they are as short as possible. They contain only absolutely focused, relevant information. And it might be that in the vector space or in the vector store, you only have in the re-ranking the top 5 documents. However, those top 5 documents are only those documents that were fed into the vector store and might be irrelevant, factually irrelevant, but they were the closest to your search query vector. And therefore you get 5 irrelevant evidence documents back. And this can disturb the performance of your LLM and lead to hallucination. So you see the interplay between an LLM and a RAG system is extremely sensitive to all those parameters I just showed you. My goodness. Okay, so in a very short summary of the first research paper, LLMs are highly receptive to counter memory when it is the only evidence presented in a coherent way here in the prompt that the RAG feeds now here our LLM. However, LLMs also demonstrate a strong conformance bias towards its own learned parametric memory when both supportive and contradictory evidence to their own parametric memory is presented here in the RAG return. In addition, it is shown that the LLM's evidence preference is influenced by the popularity of its learning, the order you provide the information, and the quantity of evidence, none of which may be a desired property for tool augmenting LLMs. And all of this can lead here to inconsistency in our AI system, and those inconsistencies manifest as hallucination. So now you understand that our AI system of today are extremely sensitive little systems. My goodness, you have to take care about them, and you have to know about their weaknesses, and you have to optimize their pre-training, their fine-tuning in their alignment phase. You have to improve the data quality significant for the final task that you want this LLM to provide in your company or for your private task, whatever. And the effectiveness of our framework also demonstrate that LLMs can generate convincing misinformation. And this poses a significant risk, not if you want to write a French or British poem, but if you are working in bioinformatics, if you're working in finance, if you're working in medicine, if you're working in health, if you're working in critical data infrastructure, in cybersecurity, you do not want that the LLM generates convincing misinformation, and therefore we have to fight here with these new insights that hallucination are generated in the very first place. But I think this would be the topic of one of my next videos. So finally, different RAG systems behave differently. And I tried 8 different RAG systems and all of them behave differently. So you go to your RAG system that you like, that you know how it works, that you are familiar, that you know its weaknesses. You test it out more, that you understand what is happening, where's the threshold when it goes crazy. And you look also at the system commands, because the system commands of different RAG systems are completely different. And some system commands, now regarding the external RAG knowledge integration only, are really different. And I don't think that it makes sense if in a system command you have accept any and every external RAG data as true and integrated in your system, or any other derivation of this. But whatever we learn from this, hallucinations are here to stay. We just have to understand the sensitivity of systems. LLMs hallucinate, RAG systems hallucinate, vision language system hallucinate. I will show you this in one of my next videos. But however, I think that a consensus is that hallucination originate if we have non-coherent systems. And non-coherent, I mean really from the quality of the pre-training data sets to the pre-training methodology, to the fine-tuning data set, to the fine-tuning methodology that is in accordance with the pre-training methodology, with the alignment instruction that are based here not only on the specific domain, but are also in accordance, coherent to the other two learning steps. And this is the way we can reduce the hallucination, because we can build more coherent LLMs and RAG system. But more about this in a later video.